Hello, guys. Welcome back to Cheenta School of Statistics and Data Science. I'm extremely happy to have Tathagata Banerjee here. I will tell you, about his work, but the best thing is that I do not know much about statistical quality control, and his bachelor's work is on statistical quality control, and I am so excited to learn from him. And I was from him in when I was discussing with him just before the meet, and I already learned a lot. I'm so thrilled to to for him to explain the topic and the ideas to you, and let's see what he has for us. By the way, Tathagata has got into IIT Kanpur this time. He has cracked IIT Jam MS, and he's from St. Xavier's College, Kolkata. And he will be presenting on this multi-sampling inspection plan, which is a kind of a generalized approach to acceptance sampling. So I will just explain a small, briefly what exactly it means. You have a big, let's see, there's a company and there are big products, like let's say Colgate, and they're producing toothbrush, not toothbrush, let's say toothpaste. And based on the toothpaste, like there are thousands and lakhs of toothbrushes produced, and based on that, how will the company decide that that products can be sold? There can be some issues, right, in the making of the whole products. So Tathagata's work is based on that, and it's a part of statistical quality control, that how to manage the quality of products made by the companies in a statistical way. And usually this is not taught well in colleges. Still, Tathagata has selected this topic. He told he has been taught well in his college. I'm so excited to learn from you, Tathagata. Sorry for the elongated introduction. It tells me, I'm excited about it. So this whole thing is over to you now. And yeah, you also told me that you will tell us a story. So just for a reminder about that. Yeah, please go ahead,
Yeah.
Tathagata. Thank you.
So basically, in this story starts from semester 4. We had inference, linear models, and the statistical quality control. So obviously, the other two papers were quite a lot of new concepts, and we need to practice a lot and devote a lot of time to that. So compared to that, SQC always seemed kind of easy to me. And when we got to this product control, SQC has two main parts: process control and product control. So when you go to product control, first we learned the single sampling inspection plan. So I'll explain more about it when time comes. So single sampling inspection plan, like our entire class, we are very happy to learn it because it's just drawing one sample from usually a binomial distribution. So we are very happy because we could do it very confidently in both theory and the practical. We are very happy that we're actually learning something which we could do instant. Then came double sampling, where we had to just draw two samples from a binomial distribution. When we are even happier, like if our entire course was designed like that, where you could draw one sample from a distribution and be happy about it, then nothing could have been better. And then suddenly one day our teacher told us that our syllabus is over, and we were very surprised. Like, and even I asked the teacher that, "Ma'am, why are we stopping at two samples? Because like I was very happy to draw one and two samples. Why didn't proceed to draw 3, 4, and go on drawing more samples and doing the same thing and being happy about it?" And ma'am told us that no, it's as we go on drawing samples, complexities increase, and that's not funny. That's out of our scope right now. We can't cover it. So from back then, I was very intrigued about it. That why did we particularly stop after 2? Like we could have just drawn more samples and been happy about it. So when the opportunity came to choose our dissertation topic in semester 5, and luckily I had the same teacher as my guide who had taught us SQC. So I told ma'am, I had asked you that question back in semester 4. Can I explore it more and go on drawing more samples myself? Then ma'am told me, yes, go proceed. It will probably be a bit more complicated, but you should be able to do it. So, and that's where I got this idea of the multi-sampling inspection plan, and here I am with my BSc project in front of everyone.
Super. Like this is like the whole project stems from a question that has been very and a source of curiosity to you. So, and I mean, this path, I think this is a very methodical approach to think about problems and their solutions. Okay, so I will not take much time. I'm very excited about this already. So please go ahead, Tathagata. Please share
Okay.
your idea.
So this is the title page, and let me proceed a bit. So this is the introduction part, which basically tells us what statistical quality control is.
Okay.
So statistical control is, as it's given in the screen, it's the application of statistical techniques to inspect the quality of a product during the process of production, which is
Okay.
known as process control, and after the process of production has been completed, which is product control. So after a company produces items, like you give the example with Colgate and toothpaste, so before marketing them, the company needs to do a check about whether the items are good enough to be produced. Like, there are checks during the process, but some checks also needed to be put in after the process is over, like just before the marketing. This is known as lot sentencing. So basically here, the items which are produced, they are divided into large lots. The lot formation is another very important topic of this, and I have not gone into very much details. We'll just consider the lots are large enough so that it's economical. And the lots are checked about whether the lots are fit for marketing or not, and based on certain decision rules. And this process is referred to as lot sentencing. So essentially, lot sentencing has three main approaches. One is 100% inspection, acceptance without inspection, and acceptance sampling.
Can I ask you a question?
Yes.
So, lot sentencing means that, just to get a mathematical idea, that let's say there's a population of products, that is, let's say Colgate makes 1,000 toothpicks. Okay.
Yeah.
So what does this lot sentencing do to that 1,000 products? What does it do?
So essentially, we have a lot of 1,000 items here,
Mm-hmm.
and there are three approaches. So in either approach, we check the lot for a specific quality. If the lot is accepted based on what lot sentencing process we use, then it goes for marketing. And when it's rejected, it's either say completely trashed away, or it can be rectified and then put it up for marketing again.
No, what I'm interested in ask, like, is the entire population of products a lot, or is a sample of the whole population of products a lot? Am I making sense?
Yeah, like so basically, like, see, if there are 5,000 toothpaste produced, so they are basically divided into 10 lots of, say, 5,000 each.
500 each, you mean?
The total is 50,000, because
Okay,
the lots
I got you. 50,000 products, you're dividing into 10 lots. Each lot is 5,000.
Yeah.
Now you're taking now. Okay, so please go ahead. Yeah.
So basically, there are the three main ways, and all the three ways have their own benefits and the pros and cons. So I am going into the okay. Give me a second. Yeah. So first is the 100% inspection. 100% inspection, as the name suggests, is just checking the entire lot of items about for checking the lot quality. So it's obviously the safest way. But the main issue is that it's obviously, like, when we the reason we do sampling, it's not economical. It's not, there are time constraints as well, and also there are some destructive populations like firecrackers and medicine pills, which cannot be used more than once. So we cannot actually use 100% sampling on those lots.
Fires? And what did you say? Firecrackers and
medicine pills. Like, if we test them once, if we use them once in the sampling process, how will we use them again in the when we have to actually market them?
Got it. Nice.
If we go for 100% inspection. And sometimes there are also sampling errors. So, but still 100% inspection is applicable when say we are dealing with very costly machinery parts. And even if we miss out on one part, then some very high cost will be involved in the later stages. So in those cases, we consider 100% inspection, but it's still a very rare and a situational thing.
100% inspection means you're checking that 50,000 each of the 50,000 elements.
Yeah.
Okay.
And then is acceptance without inspection, which is another extreme, that we blindly accept all the lots. And this is obviously there's no cost involved, but this is again very impractical. It's only usable when, say, the producer has very good reputation, and then we don't need to check it, or we are going short in time or something. But again, this is not a very practical method.
Just blindly accept everything.
Yeah.
Okay, then what's the point of doing the quality control?
Yeah, exactly. Say because this is the process of product control. So process control has already been applied before. Say we have done the process control from a very reputed company who have like 99.9% times they give us good items. So then this doesn't make sense. But it is very impractical because these won't usually be the case. So acceptance sampling is kind of a middle ground between these two, and this is the which it is most widely used.
Yeah. So you're going to explain what is acceptance sampling?
Yeah. So acceptance sampling basically involves drawing a number of samples from the lot of given items and deciding upon the lot based on the results of the given samples.
So can you give, I will ask you, I will request you to give or explain with respect to this 50,000 examples that you have given, like initially 50,000 are divided into 10 lots of 5,000 each. Can you explain in terms of that?
Okay, so I'm going with single sampling because that's the easiest thing.
Sure.
So say we have the first lot of size 5,000. So we draw a sample of say size 30 from it.
Okay.
And we check for the number of defectives in the size sample of size 30. So we have a rejection number, which is a given threshold value, usually known from past studies. Say in our case, the rejection number is 10.
Okay.
So if in that sample of 30, the number of defective items is less than equal to 10, then we can consider the entire lot to be conforming, like it fits our standards, and then we accept the entire lot. Otherwise, if the number of defectives is greater than 10, we reject the lot.
Okay. So is this point of 10, is it decided by some testing of hypothesis thing?
Yeah, this is actually often pre-decided based on previous studies.
Okay.
And yeah, there are some parameters which called consumer's risk and producer's risk, which usually end up defining this rejection number.
Okay. Got it.
So now acceptance sampling, the advantages, obviously compared to 100% inspection, it's less expensive, and as it doesn't have the disadvantage of not being applicable to discrete populations, we can easily apply it to there. And it also greatly reduces sampling error. And obviously it's more reliable than the without inspection thing. Disadvantages?
Yeah. I have a small question. It's a beautiful explanation. I understood these three aspects. The question is that those out of this 10 lots of 5,000 each, you're taking 30 from the first lot. So the decision is, so what is the decision? Is it like
we accept the first lot?
Okay, we can accept the first lot. That's what the decision is, not the other lot.
Then we go for the second lot again, and we just repeat this process.
Okay. So it's individual lot inference.
Yeah.
Okay.
And the lots are usually drawn in such a way that they are homogeneous. Otherwise, it won't make too much sense.
So homogeneous can be done by randomly picking up things, right?
Yeah, or say we have among the 50,000, say 3,000, 30,000 are made by Colgate and 20,000 made by some other company, and we are marketing both of them. So we will obviously put the Colgate ones in one lot and the ones by the other company in another lot.
Oh, okay, got it. Yeah, then it cannot be done randomly.
Exactly. So
Yeah.
that has to be kind of, I think, purposive or stratified, I guess.
Okay. Yeah.
So yeah.
Sorry. I personally have a feeling that this whole sampling procedure have a very in-depth connection with survey sampling. Like,
Yeah, I think so too. Because usually in our problems, we are given the lots. So we proceed from when we have the lots and we consider the lots as kind of a population. And from that, we do the sampling. But the lot formation is an entirely different topic, and it's a topic that I don't think has been very widely explored. How to
interesting.
exactly form the lots, that's an entirely different question.
I think it's interesting. I mean, students out there who are really looking for BSc projects or ideas, I think can explore this part. Like, how is the selection of the lots related to survey sampling? For example, this stratification idea is kind of like selecting lot is kind of like stratifying into various like homogeneous things. So that's what I'm thinking. Like, maybe there is some connection. I don't know. Like, I just felt. Yeah, please go ahead. It's very exciting,
So
interesting.
the disadvantages, it's obviously compared to 100% inspection, we obtain less information about the product or the production process because we don't draw all the items. And also it involves risks of accepting bad lots and rejecting good lots, which is not present in 100% inspection. And these risks, they are actually two very important parameters known as consumer's risk and producer's risk in the acceptance sampling process, which we'll go into more detail later on.
Okay, so this is like type 1 and a type 2 error. Okay,
it's exactly analogous to type 1 and type 2 error. So the acceptance sampling plan is obviously needs to be very carefully chosen and planned based on the history of the producer as well as our future aims. Like what do you want to get? Like, do you want to provide more protection to the consumer, or do you want to provide more protection to the producer and go for like low cost things? So
interesting.
Next is lot formation. I've gone into here in very less detail. Lot formation needs to be very properly done because after we draw the lot of items, we go for acceptance sampling. So the lot formation is kind of the primary thing here. The lots should be homogeneous, which I just discussed, and larger lots are preferred over smaller ones because more economically efficient. Like in our example, if we had considered 100 lots of size 500 each, then we have to check for all 100 lots. That's obviously less economical than going for 10 lots.
True.
And after the lots have been formed, we can go for appropriate random sampling techniques to go for acceptance sampling. Now, there are two main categories or schemes of acceptance sampling. One is the acceptance rectification scheme, where after the lot is rejected, the defective items in the lot are rectified and then marketed again. And the second one is acceptance rejection scheme, where after the lot is rejected, we completely dispose it of and don't consider it again.
Okay. So it's like, yeah, I think this is very similar to sampling. Like yeah, it's a similar to like, that's why the name probably, yeah.
Exactly. It's kind of a particular type of sampling.
Yes. So please go ahead.
There are some terms and notations which we'll be using. So capital N is the size of lots in which products are manufactured, and P is the proportion of non-conforming items in a lot of size capital N. So it's known as lot quality or lot description. And it's usually this P is kind of known from beforehand, or at least we have considered it here to be known from beforehand because we have a product quality history with the producer. So P for different producers is usually known. So
P, the smaller the P is, the better is the product quality.
Exactly.
Okay.
So process average P bar, say there are M lots and ith lot Pi is the proportion of non-conforming items. P bar is just the arithmetic mean of the Pi values.
Okay.
So obviously price average higher means lot quality is poorer and vice versa.
Great. Okay.
Next is average quality level, which is the highest value of price average, which is acceptable to the consumer. It's kind of an upper bound to the allowable PR values.
I mean, how bad it can go, that is the like
That the
no, it's the
consumer
highest
can
value.
still
It's like
accept.
the maximum order statistic. Like not a statistic, but yeah, it's like max of all the PIs.
Kind of like the level of significance, like how much level we can, like how much type on error we can allow.
Okay, okay, makes sense. Interesting. Yeah.
Then is lot tolerance percent defective, which is highest value of PI in a particular lot that is acceptable to the consumer. Like P bar is the highest value of process average that is acceptable to him, and PI is the highest value of uh, non-conforming items in a particular lot that is acceptable to the consumer.
Okay.
It is known as the lot tolerance percentage defective, LTPD. It is usually expressed as a percentage, 100 to PT percent, and usually PT is greater than P and P bar.
Okay. I'm confused about this AQL and LTPD. Like usually the lot percentage level should be the same, right? Like
No, like say we have say 10 lots, and say the number of defective items are say 5, 10, 15, 20, 25, 30. Okay.
yeah.
And the consumer wants that the entire process average should not be very high, say 15 or 20.
Okay.
So and LTPD is that the highest value of P for a particular lot. Like even if a particular lot goes kind of wrong, if AQL is less, that is the mean is less, then the lot can be accepted.
Okay, okay, okay. But this but this AQL is found out over the 10 lots, right?
Yeah.
But if it's found over the 10 lots, okay, so it's like AQL is found out over the 10 lots, the average of all the P's, right? No, I'm just
Yeah,
getting problem.
it's kind of the say the upper bound to the mean, and LTPD is the upper bound to the highest order statistic.
No, wait, I'm not understanding. Can you go above a bit? Like I'm trying to understand the intuition of this. So process average. So let's take 3 lots, okay?
Okay.
For the first one, each one of them has 100 elements. 100.
Okay.
In the first one, there are 5 bad items, non-conforming items. Second one, 15. And third one, 20.
Okay.
So, or let's say 20. Yeah, 20. So the process average is 5 plus 15 plus 20, like 0.05, 0.15, 0.25.
0.2. So it's 0.4 by 3, like 0.13 something.
Yes. Yeah. 0.13. Okay. So that's the P bar, right? Process average.
Yeah.
So can you explain what is AQL and LTPD in terms of this?
Say here AQL is 0.1. Say let's go with 0.15. Then the P bar is less than AQL.
No. How do you find out AQL?
AQL depends on the consumer's preferences.
Oh, okay. AQL is set up by consumer, not related to the process.
No, not at all. AQL and LTPD both are set up by the consumer.
Oh, okay. Yeah, please explain. Yeah, let's say it's 15.
Say AQL is 0.15. Then even if one lot has more non-conforming items than 0.15, the 3 lots together are still accepted, because here the average is 0.13.
Oh, okay. Interesting.
And say the LTPD is 0.25, and since all 3 are less than LTPD, the lots get accepted. So these are like 2 different checks.
But if it's 0.15?
There's the AQL.
Yeah, 0.15 is AQL. Let's say LTPD is 0.15. Then
the lot then it won't be accepted, because in one of the lots the price average is greater than the LTPD.
Okay. Got it.
Okay.
Yeah, got it. Okay, thank you.
Yeah, definitely. Next up is the OC function. The OC function gives the probability of accepting a lot of quality P under specified sampling inspection plan. So it's basically the probability of acceptance of a lot given the proportion of non-conforming items in the lot is P.
Okay.
It's denoted by LP. So LP versus P, this plot is known as the OC curve. And it's a very commonly used curve to denote a sampling inspection plan. And it's
Okay,
also
let's
used for
understand.
competing sampling inspection plans.
Sorry. Yeah, I understood what like the definition, but let's understand with respect to this example. So these three lots 0.1, 0.05, 0.15, and 0.2. So in this, how will you plot the OC curve, OC function?
Okay, so let us consider, say, P, the first lot with P is equal to 0.05. We go for a particular sampling inspection plan and obtain that LP is, say, 0.3. So we take a 0.3, 0.05, and then we go for the second lot. We, with P is equal to, say, 0.15, we obtain LP. And for the third one, we do the same thing. We get LP for the P, and then we join the 3 points. So OC function is not a property of a lot, it's a property of a particular inspection plan.
Okay, so P is on the x-axis, right?
Yeah.
And L is on the
y-axis.
So is there a mathematical way to calculate this LP?
Yeah, definitely. Like for each sampling inspection plan, LP varies. And this LP calculation is actually a massive part of my project.
Okay, I got it. So LP calculation is the probability. So depending on, so every, let me understand Tathagata, because I am very new to this, I don't know this. So it's LP. So there is different sampling procedure, induces different distributions or different modeling, and different modeling leads to different LP.
Exactly.
And based on this different LP, somehow use this LP to use that which modeling is better, which sampling is better than the other, probably.
Yeah, like for different values of P, we obtain LP, and we say we can tally them together by overlaying them on the same graph.
So I see that line it's written that for a slight increase in P, the probability of accepting a lot decreases.
Yeah.
Can you explain this last 3 lines?
Okay, so for the OC curve is a decreasing curve because as P increases, LP decreases. Because as P increases, the lot quality goes on falling, and so probability of accepting the lot goes on decreasing.
Yeah, got it. So as P increases, the lot quality falls, and hence the probability very good. Yeah, absolutely makes sense. Yeah.
Okay, so as P increases, like for most practical processes, like for P is equal to 0.3 and 0.4, like when you go to those values of P, the LP curve kind of reaches close to 0 and flattens out.
Okay.
Because 0.3 and 0.4 are very bad lots. Like if a lot has like 4 bad items out of 10, it's a very bad lot. So the curve kind of mostly has fluctuations between 0.01 to say 0.3, and thus for a very slight increase in P, the LP goes on decreasing, and steeper the OC curve, the higher is the protection provided to the consumer. Because with slight increase in P, if LP decreases by a lot, then the consumer has a better chance of getting better items.
Yeah, you're right. Absolutely. So the the higher the steepness of the curve, that means the lower the area under the curve.
Kind of, but not always, because sometimes, like for some plants, it can abruptly go on, like abruptly steepen or change at some points. So the area under the curve is not always not a very good measure unless one is like completely above the other.
Okay, makes sense. Yeah.
But it's still kind of give us a visualization about the entire sampling plan.
What is this consumer risk?
So first, the definition of a consumer is there. A person who receives a manufactured products is referred to as a consumer. Like we are all consumers.
Yeah.
So after the acceptability sampling process, the consumer has a risk of receiving a bad lot because of the sampling. Say in the sample we get a good result, but actually the lot is not that good. So it is usually denoted by LPT, like is a value of the OC function where P is equal to PT. Since PT is LTPT, which is usually considered a bad value for P. So it is denoted by LPT. So, and usually the sampling inspection plan aims to provide maximum protection to the consumer because the consumer is more important. So consumer's risk is very often selected as a parameter in obtaining the optimal sample sizes and other plan parameters. It's kind of like fixing the level of significance. So next up is the producer sample.
Can you go above a consumer risk? So consumer risk is the probability of accepting a sample of
poor quality, a lot of poor quality.
So at that T, at PT, so if you consider the curve, OC curve at PT, that is the consumer risk. The LPT is the consumer risk. The PT height of the function is the consumer risk. And can you go down? And procedural risk is?
It's producer's risk. So
it's 1 minus LP bar. Like it's taking the average of all the, kind of average of all the.
Like P bar is considered to be a good quality because it's the average of all the non-conforming items in the lot. So P bar is considered to be a decent quality lot, and hence its producer's risk is the risk of rejection of a good quality lot. So it is 1 minus LP bar.
Got it.
There is 1 minus value acceptance. So next up is the API or ASN, which is the average number of items that are to be inspected from a lot under a particular inspection plan to decide whether to accept the lot or not. So it is referred to as ATI for the acceptance rectification scheme, and for acceptance rejection scheme, it is referred to as ASN. And since in this study I have used acceptance rectification scheme throughout, I'll refer to as ATI from now. And keeping the other factors fixed, lower the ATI, better the inspection plan, because the producer has to review less items, and thus there's some economic efficiency.
In his part. Very good.
Now the OC curve obviously lies from between 0 to 1, because 0 less than equal to P less than equal to 1, and 0 less than LP less than equal to 1. So there are 4 points that are usually considered to be important: 0, 1, 1, 0, P bar 1 minus alpha.
Makes sense.
PT beta.
Got it. PT is fixed before, right?
PT is
I forgot. What is the PT definition? It was initially defined by the.
PT is the LTPT, which is the upper bound for the worst lot.
Got it. Perfect.
So
so these 4 points are important, and we join that to get the curve, LP curve, OC curve.
Like we don't exactly join. We actually obtain LP for a lot of values of P, and then we join all of them. But these 4 points are the 2 extreme points and 2 important points, because producer's risk and consumer's risk are of a very high importance to us. So these 4 points are usually looked at when we go for a OC curve. So the objective of the study is to theoretically formulate a multi-sampling inspection plan, obtain the OC function, and compare a multi-sampling inspection plan to a corresponding single or double sampling plan, and discuss the advantages and disadvantages of using a multi-sampling inspection plan. And we always
what is this multi-sampling thing?
Multi-sampling. So I'll get into multi-sampling a bit later, when we need to first go to single and double sampling.
Sure.
So, and throughout we keep the consumer risk fixed at a well, because it's a planned parameter and it's of utmost importance.
The beta one. Sorry, the alpha one.
It's beta. Producer is alpha.
Yeah.
So there are a lot of types of lot sampling inspection plans. We are considering 3 of them here: single sampling, double sampling, and multi-sampling.
Okay.
Throughout, we have assumed that the lot size n is larger than the sample sizes at all stages of sampling, as well as the cumulative sample sizes. And we have also considered the acceptance rectification scheme.
Sure.
So first, we go for single sampling, which is the most simple one. So here we basically have a lot of items, and we draw a single sample. And if the number of defectives in the sample is less than or equal to a threshold value known as the rejection number, we accept the lot. Otherwise, we reject the lot. So here is some notation.
In single sampling,
Hmm.
you take out from a single lot.
In all of these, we take out from a single lot only. Like
Okay,
we will just repeat this for all the lots.
So there are n elements, capital N elements in the actual lot.
Yeah.
And you take up small n elements one by one.
Yeah.
So where is the single part coming? One by one, like
there's only one sample.
Okay, one n length one
N is
n
the
amount
sample
sample
size.
is taken. Okay.
So we only draw one sample. So that's the single part.
Okay. Got it. Yeah.
So D is the number of non-conforming items and C is the sampling number. If D is less than or equal to C, we accept the lot. Otherwise, we reject the lot and rectify or reject it. So the probability distribution of D. D is the number of non-conforming
D is the
number of non-conforming items in the sample.
Okay.
So since
and
we draw
C is the
sampling number. If D is less than or equal to C, we reject it.
Number? I forgot.
If D is less than or equal to C, we accept the lot. Otherwise, we reject the lot.
Yeah, but what is sampling number?
Like sampling number is C, the maximum allowable number of non-conforming items in the sample.
Okay. Yeah. Okay. I missed that definition. Okay.
So D is the number of non-conforming items in a sample of n items drawn from a lot of size n with P. So D follows hypergeometric n, capital N, small n, P.
Absolutely.
Now, since we have assumed that capital N is very large compared to small n, which is very often done in practice because we consider large lots. So D follows binomial small n, P.
Yeah. So it's like yes. So you're taking out, since the large population of the lot, you're taking out each sample, which is a probability of like P of being bad.
Yeah.
So D is the number of makes sense. So D is the got it.
So the OC function LP is given by probability D less than or equal to C given P, and consumer switch beta is just LPT. So I've just written it down in terms of the binomial PMF.
Perfect.
Now we have to calculate ATI. Y1 is a random variable, say denoting the number of items to be inspected in the SIP. And the PMF of Y1 is given in this table. Y1 takes value small n if probability T greater than C, that is LP, and takes value capital N otherwise.
Can you explain this? I didn't understand Y1.
Okay, so Y1 is the number of items to be inspected. Okay. Say we draw a sample of size small n and we say accept the lot.
Okay. So ATI is expectation of Y1. Exactly. Okay. Average total inspection. So YI is the total number of items to be inspected in that single sampling plan.
Yeah. Okay. So Y1 is a given sample, and so expectation Y1 is the average total inspection.
So the probability Y1 is equal to Y is asking that what is the probability that small y is the number of samples, number of items to be inspected.
Exactly.
So the sample size is Y? I'm confused.
No.
So inspection is like we are taking out a sample of size n,
Yeah.
small n.
Say y1 is a random variable which denotes the number of items to be inspected. Okay.
Okay.
Now, say we draw a sample of size small n, and if we accept the lot, we don't inspect anymore. We don't like inspect or rectify any more items. And
Yeah.
with probability LP, the number of items inspected is small n. And if we reject the lot based on the sample, we go for rectification. So we have to basically, in the rectification process, we go on inspecting the entire lot. So with probability 1 minus LP, the number of items is capital N.
Okay, let me understand. I think this is a bit interesting. So that's it. Let's say we have 10 lots of 5,000. Okay. Yeah, I'm making you talk a lot. Sorry. I should also drink some water. So there are 10 lots of 5,000 each. So we are taking a sample size of 100. Okay. So LP is the probability. So now understand, now let me teach me what is this y1, what is the number y, what is the random variable y1, that and make me understand that.
Okay, so basically the number of items that are to be inspected in a SSIP is a random variable. Okay, it can take only two values. One is small n, one is capital N. This is because say we have a this example with lot size 5,000 and
okay, it can only take two values. I didn't know that.
Yeah, it's given the PMF here. See.
Yeah, I mean that's what I'm trying to understand. That if it's just checking the small sample, that's okay. If we do not check the small sample, then we check the entire lot.
Yeah, because after we say we accept the lot, then we go for the small sample and we're happy. Okay.
Yeah.
If we reject the lot, since we are considering the acceptance rectification scheme, we have to basically inspect all the items and rectify them.
Okay, got it. Okay.
So if the lot is rejected, we have to basically inspect all the items in the lot
and make changes. Let's say there is some break in the Colgate toothpaste
exactly.
cover, so we have to change it. So that is what is inspection. Okay.
Go through the entire lot. So basically, the number of items to inspect is a random variable which takes two values, small n and capital N. If it's accepted, we just go for the sample, and it's not, we go for the entire population.
Perfect. Very good. Got it. Yeah.
So API is just the expectation of y1, which is I've just computed it. So
very good.
It comes out n minus n into LP.
Yeah.
And under the larger approximation, since small n by capital N is negligible, this ATI can be approximated to n into 1 minus LP. So that's the ATI for SSIP for a given P and capital N.
Got it. Very good.
So next we proceed to double sampling. So in double sampling, first we draw a sample from a lot of products. Then depending on the sample, we can either accept the lot, reject the lot, or draw another sample.
Okay.
And then on the basis of second sample, we accept or reject the lot. So there is just some notations where it's similar to the earlier one. N is the lot size, and N is just N1, N2, D1, D2. These are the new things because earlier there was only one. So now it kind of defines the scheme. Say if we are considering the first sample, if D1 less than equal to C1, we accept the lot.
Yeah.
If D1 greater than C2, we reject it. And if D1 lies between C1 and C2, if C1 less than D1 less than equal to C2, we draw a second sample.
Okay.
Because we are kind of inconclusive from the first sample, so you need a second one. Now, if D1 plus D2 less than equal to C2, we accept the lot, else we reject the lot.
Great. Got it. Perfect.
And we also assume that n is large compared to n1 and n2, as well as n1 plus n2.
Mm-hmm.
So we find the distribution of d1 and d2. So d1 obviously follows a hypergeometric capital N comma small n1 comma p, and d2 given d1 follows hypergeometric n minus n1 comma n2 comma p star. Because after the first sample has been drawn, the population size changes and the proportional defective also changes.
This is a very good example of conditional probability. Like, to the students who are seeing this and you're still learning, students of Cheenta and others in Cheenta, we are currently teaching conditional probability. So for this idea of conditional probability is very important. Like, it's D1 is fixed, so you can see a sequence of steps. And based on the previous step, the next distribution is what is the conditional distribution and conditional probability. Thank you. It's a very good example. Please go ahead. Yeah.
However, because of larger approximation, we didn't have to need the conditional thing, because for the larger approximation, n minus n1 is approximately equal to n, and so p star is approximately equal to p, and the two samples can be considered to be independent, because we are considering that the total sample size is very large. So we're basically drawing that first n1 samples does not make much difference. So d1 and d2 are following binomial n comma p and n comma p distributions independently.
Yeah. So I will tell the students out here why you can mathematically show it's independent, because of that step. You see that D2 is dependent upon D1 via the probability only. So the probability goes to P. So there is no D1 out there. So hence D2 is independent of D1.
Size also changes, but that also can be approximated to capital.
Exactly. So you're approximating that NP minus D1 by N minus N1 by P. Hence the D1 goes away. Hence it becomes independent mathematically, right? Okay, perfect.
So D1 and D2 are independent. So D1 plus D2 follow the binomial N1 plus N2 comma P distribution.
Perfect.
This is a property like everyone knows from SEM3, I guess.
Yeah.
So the OC function LP is L1P plus L2P. But L1P is the probability of accepting the lot after drawing the first sample, and L2P is a similar thing for the second sample.
Got it.
Now we compute L1P and L2P. Okay.
So this is defined, or this is defined like this?
We define which one is defined.
Like
the OC function.
The LP, yeah, it's defined already, right? So you can prove that is equal to L1P plus L2P?
Yeah.
Just thinking how. Probably by conditional probability. That's what I'm thinking.
No, because we are accepting the lot based on the first sample. That probability is completely different from accepting the lot based on second sample, right? Because we are just drawing a number of samples, and in each step we have a probability of accepting. So the total probability of accepting is basically sum of the individual steps, because we are actually considering the conditioning thing through the conditional distribution.
So probability of okay, I understood. Probability of accepting is equal to probability of accepting in the first lot plus probability of accepting
in the second lot, because there's no other way the lot can be accepted, right?
Yes, because so probability of accepting, so you can, like, using law of probability, you can see like this, that it's just for the students, okay, so that who are just learning probability. So probability of accepting is equal to probability of accepting given first law, given that it's accepted in the first law, in the first sample, plus into probability, it's like probability of acceptance intersection first sample plus probability of acceptance intersection not first sample. Now, not first sample can be expressed as second sample. Yeah. Because second sampling is rejection of first sampling, but acceptance of second sampling.
Exactly. So we don't go to the second sample if the first is accepted on the first sample.
Got it. Perfect. Please go ahead.
So L1P is probability D1 less than or equal to C1 given P, and I've just written it down in terms of summation. And L2P is actually the joint summation. So it is probability D1 plus D2 less than or equal to C2, comma C1 less than D1 less than or equal to C2 given P. So it's accepted based on second sample, and in the first sample, it couldn't have been either accepted or rejected. In the first sample, it needs to lie in this range, so we can actually draw the second sample.
Got it.
Okay, so I have just expressed it in some double summations, and I have kind of simplified it. And because of their independent, if they're not independent, the expression would have been very clumsy, the final expression.
Absolutely.
So I have basically obtained L2P, and the consumer is P, beta is equal to LPT, which is L1PT plus L2PT.
Got it. Yeah.
Now we compute the average total inspection ATI. So similarly, like the earlier one, we define Y2 as a random variable.
So ATI can be like N1 plus N2, and capital N. Okay, got it. Yeah.
Small N1, N1 plus N2, and capital N. Yeah.
Great.
And the probability notations are given here. Like, we can accept it based on the first sample with probability L1P. So Y2 takes N1 with that value. And we can accept it based on second sample with probability L2P. So that takes N1 plus N2. And otherwise, we go on rectifying all that. And so that's capital N.
Perfect. Yeah,
so,
this, I mean, of course, a student cannot understand this just right at this moment, but they can understand the idea. Okay, we are calculating the expectation, we're calculating this probability. I think the student can get in touch with you, Tathagata, after this, and if that person wants to know furthermore, that student can get in touch with you. And I will share Tathagata's LinkedIn ID in the YouTube description, so that student can get in touch with him and discuss about further projects that the student can do and get ideas from Tathagata. It will be a great value addition to the students by Tathagata, and he would love to do that. I know that. Yeah. So now he finds out, you're finding out the expected value of this Y2. Okay.
Yeah, that's the ATI for DSIP. So I'm just basically adding the Y2 into probability Y2 minus Y equal to Y values. So that comes out to be this expression. And under the large lot approximation, where N1 by N and N1 plus N2 by N, these are considered to be small, the expression comes out to be N into 1 minus LP.
The same thing as before, right?
Yeah. So basically, for a fixed N, the ATI depends on just the LP. Okay, and spoiler, this is also true for the multi-sampling inspection plan.
You shouldn't have given the spoiler, but yeah, just joking.
Okay. So next.
But yeah, it's good. So you're showing this. So this is a very important result that you can show. So it's a really good thing that you have shown this. Like, why didn't, like, is there such a work in the, in the academic research based on this, or like, I mean, you can easily publish a paper based on this in any, if it's not done before.
Actually, I couldn't find much material about this. Like, I went through 2 or 3 books, but in those places that the multi-sampling inspection plan is kind of mentioned, that it's an extension of double sampling inspection and it's beneficial in some way. But I never knew what the way was before I did the project myself.
That's great. Super. I really appreciate it. You have done all the calculations yourself, right?
Yeah. Like, at a point, I was very confused. And I asked my supervisor, ma'am, like, what's the benefit of doing this? I just formulated theoretically, but I can't find the benefit. Like, I need a lot of time to actually find the benefit. Like, and to compute the ATI, I actually had to just like derive this theoretically, and I was confused what to do now.
Okay, please go ahead. So you can, like, this is my suggestion. You can just tell us the idea, because the idea is the same. The main is the sampling procedure. That is the main idea. That you select N1, then N1 plus N2, then N1 plus N2 plus N3, or N1 plus N2 plus NK, right?
Yeah.
Tell us the basic idea. You can skip the proof, because you can say the main results, because the proof, the students will not understand as it is, like, while watching this. So
yeah,
you can share your work later on if you want to, publicly, or then you can share it on LinkedIn and can share that link to the students for them to get into this stuff deeply. But please explain the procedure, what you have done.
Yeah. So basically, it's an extension of DSIP where we draw maximum of K samples from a lot. We call it a K-type inspection plan. So capital N is the lot size, and we're going with similar notations with just NI, DI, and CI, which is the size, number of non-conforming items, and the external number based on the ith sample, I from 1 to K. So we are let us consider the general ith sample, and we compare the values of summation dj, j from I1 to I, that is the cumulative number of non-conforming till the ith stage, ci and ck.
Okay.
Okay, and this MSIP, the plan is not unique. Like, compared to single sampling and double sampling, the plan is not unique. You could have gone for like changing the upper limit at each stage and fixing the lower limit. I have gone with fixing the upper limit and changing the lower limit at each
What is
stage.
this upper limit, lower limit?
Like the upper limit, that by that I mean if summation dj, the cumulative number of non-conforming, is less than or equal to ci, we accept it, and if it's greater than ck, we reject it.
Okay.
And otherwise you draw the next sample. Now someone could have gone for like summation dj less than or equal to c1 and summation dj greater than some ci plus 1. Like, I have fixed the upper point. Like, no matter what I ck is fixed, but ci goes on varying.
Got it. Okay.
So that can be an alternate plan, and these two plans can be compared. That's
interesting.
another idea.
Yeah, students can get this idea. Like, the students can extend his Tathagata's idea to two different multi-sampling plans based on this upper bound and lower bound, and can compare them. That can be really good work. So that's like a checkpoint for the students here to talk to him. Yeah.
So we assume that NA is very large to the NI values, and also the summation NI I from 1 to k. So we have the similar logic with double sampling inspection, that DI follows the binomial NI comma P independent of other DI values I from 1 to k. So summation DJ follows the binomial summation NJ comma P distribution.
Yeah.
So the OC function LP is summation LIP. LIP is the probability of acceptance at the ith stage. And I have now computed L1P, L2P, L3P, and I have generalized L3P to LKP. It's a very complicated summation. I'm not going into it. You can extend this with the double sampling idea.
Yeah.
So confirmation L is given by LPT, which is summation LIPT. Now let us compute the ATI, and we consider it to be YK, the random variable, which is the number of items to be inspected. So the PMF of YK now takes on a lot more than like large number of values, N1, N1 plus 2, N1 plus N2 plus N3, up to summation NI and capital N. And the logic is similar to the SSIP and DSIP one. Like, if we accept it on based on first sample, you draw N1. On the second sample, you draw N1 plus N2 and so on.
Got it.
So ATI is basically expectation YK. I have written down all the probabilities and multiplied them. And under the larger approximation, you can see all of the first terms kind of vanish because they're kind of very negligible compared to the last n term. And so the ATI-K also turns out to be n into 1 minus LP.
Interesting.
So for large lot approximation, the ATI is same for any sampling inspection. For what a K is 1, 2, 3, whatever.
Great. What's next?
Next up is comparison between sampling inspection plans. Okay. I have some OC curves here, but it's I need to zoom out of it. It's kind of difficult to compare them from here, I guess. Yeah. Because OC curves usually need to overlay, but I can't overlay 6 curves.
Did you simulate this?
No, I didn't simulate this. I have the p values from 0 to 1. Like, I had a range of 0 to 1 with, say, like 0.025 difference. I had a sequence, and for that sequence, I obtained the LP values. So I had a function. I have the entire R code is attached at the end. So I had a function which computed LP for P for a given sampling inspection plan, and I just computed the LPs for the different Ps and the different number of samples.
So how did you compare these methods?
Okay, so on the basis of OC curves, it's a bit difficult to compare because I can't obviously overlay all the 6, but let us go for, say, 1 and 6. Okay, it kind of seems that like it's a bit difficult to observe as from here as well. So 1 and 6, the curve at 1 is kind of steeper. So L for most values of P,
But curve
LP,
6 looks steeper, right?
yeah,
Curve 6 looks steeper, right? Because it is a constant bit and then it goes down steep.
not real, because at the curve 6 there's an initial like just some high LP at the initial points. I think that's how it's seeming.
Yeah. So
Because
what do you define? How do you define steepness?
I kind of define it's on the basis of the slope. So
Yeah, I mean slope at where?
I just observe the entire curve and define the steepness on basis of that.
Okay.
But
Yeah,
it's
please go
kind
ahead.
of,
Please go ahead.
so for the OC for this, I won't compare it very well. Like I can't really compare it very well from this, because the 6 OC curves, it's very difficult to observe, just observe and understand. So let us just proceed a bit to a bit further, where we can understand it better based on other measures. Okay, that's why
Yeah,
I've
got
gone with so much detail about the ATI, because the ATI is going to be very important next time. Okay, so here is the to compare the different inspection plans. We obtain the ATI for the single, double, and multiple inspection plans with K is equal to 3, 4, 5, and 6.
So you don't use an approximation there. In all the cases, ATI came out to be n into L1 minus LP, right?
I don't get you.
In all the cases, it came out to be n into capital N into 1 minus LP, right?
Yeah,
So
it's
it
based
is.
on the larger approximation.
Oh yeah, you are not doing the larger approximation here for
No, I'm
computing.
still doing it.
Okay.
Larger approximation is always there.
Okay.
So we have gone for computed the ATI for a fixed value of consumer's risk. Like earlier we had the theoretical values, and now I'm actually getting the numerical ones. Okay, so K is 3, 4, 5, and 6, and I have limited myself to 6 for a particular reason, because higher values of K might lead to violation of the larger approximation.
You're right.
Because if we have like 10 samples, the cumulative sample size may not be very small compared to capital N, even if the individual sample size is small.
You're right. Absolutely. Makes sense.
K is equal to 6. Sorry. Yeah. So, and without loss of generality, I have assumed that the sample size at each stage is fixed and CI at each stage is fixed.
Okay.
So rejection number is given by CK plus 1, that is K into C1 plus 1. Now I have obtained the ATI for varying proportion of non-conforming items and number of samples.
Okay.
I varied P from 0.05 to 0.2. Throughout, consumer is fixed at 0.05 and CI is fixed at 2. And I have obtained the values for the of ATI for differing P and differing K.
Okay.
Okay, and they are also plotted in this graph. Okay, so now we can observe.
So this is for K is equal to?
The K is on the x-axis.
Okay, got it. Yeah.
Okay, so let us first consider a fixed P, say 0.05. Okay, so we can observe that for 0.05, the ATI actually goes on decreasing as number of sampling decreases.
Yeah.
I mean increases. Sorry. So, there's also a logical explanation, since ATI is n into 1 minus LP, right? Now, as we increase the number of samples, in each step, there's a cumulative effect of the probability of acceptance. Like at each stage, we have a probability of acceptance. So if we just go on doing the sampling more number of times, there's some probability of acceptance being added on each time. So at the higher stages, LP is more. So n into 1 minus LP is less.
Got it? Yes.
So ATI decreases for a fixed P. And we can also see that as P increases for a fixed sample, a number of samples, say for the SSIP, as P goes on increasing from 0.05 to 0.2, the ATI goes on increasing. This can also be explained because as P increases, LP decreases because the lot is obviously getting poorer. So the probability of accepting kind of decreases. And that's why ATI, which is n into 1 minus LP, goes on increasing.
Mm.
And there's also another thing. I'll like to show you the table. Could you observe something about the values as P goes on increasing? Like say go for the last 3 columns. Say
The values increases of the ATI.
something else. Okay, so the values kind of go on converging to a value. Like they appear to converge somewhere. Like see the first 3 for 0.05 is 849, 764, 698. So there's still a very significant decrease. But for 0.2, it's 3671, 68, and 67. So the value is almost fixed.
So what you mean is that after a certain point, the decrease is becoming slow. The
Exactly.
change, yeah. So there is a steep point where it suddenly take a steep, change, and that's what probably is your good inspection value, like number of sampling value.
Yeah. So basically, say for 0.2, if we like going for a 4 sampling inspection and 7 sampling inspection is kind of same thing, because we don't get much benefit with increase in K. Now, this can also be explained because since P is high, the LP at each stage is very low. So even if there is a cumulative effect, at each stage LP is low, so the cumulative effect is not that much.
Got it.
So the number of samples also needs to be determined based on P. We can't just go on blindly increasing number of samples and expect the.
So how did you decide the number of samples here?
I didn't get you.
How do you decide the number of like which sampling scheme is better now? Like
we can do that, but I guess for a preliminary way, we can go for observation. Like for 0.05, we can go for 6 because we can see that ATI has a kind of a steep decrease for 0.05. But for 0.2, we can stop at 3.
Can you show the graph? Can you show the graph and explain?
Yeah, sure.
So for 0.05,
the graph goes on decreasing.
Yeah, but so, as P increases, for example, okay, as P increases, it's like the main decrease happens at 2.
Yeah, at the early stages. So and it kind of flattens out at a point. So increasing K is not very beneficial because to increase K, we need to go on drawing samples and stuff.
So that's why probably double sampling is where people stop, because for higher P values, 2 is the like comes out to be optimum. Probably can you prove that mathematically? I don't know, like, but
not sure. Like I can explain it logically, but I'm not sure how to mathematically show this.
So what I'm thinking is this: that we are all assuming n into 1 minus LP. So in the LP calculation, probably you can show that the rate of DLP or DP, the rate of DLP. Oh no, it's happening with respect to small n. Okay, no, we cannot show that with respect to that. So we have to show that this this ATI is decreasing with the number of it's hard to show.
Yeah, like I even explained it logically when I defended this project, but I couldn't solve it mathematically. Like because it's a lot of binomials, like a lot of cumulative binomial sums. How do I even go about and solve it?
Yeah. Okay, so 1 hour has already gone by, and I think we need to wrap it up right now. Anything interesting you want to share about this project, or this is where it this is the multi-sampling thing ends here?
the multi-sampling thing kind of ends here. I just have another graph. So I've just explained what I said here.
Perfect. Yeah.
So there's another graph which is ATI for varying rejection number and number of samples. It's way more intuitive than the last one. So I have fixed P at 0.05 and I have obtained the ATI for varying rejection number and number of samples.
What is the rejection number? I forgot.
Rejection number at each stage is the number based on which we decide whether to draw the next sample or not. So like if
got it. Okay. Yeah.
That is the sampling number. It's also called the rejection number, same thing. So here I have the graph. So basically we can observe here that similar to the earlier one, for fixed rejection number, as we go on increasing the number of sample, ATI decreases. So it's kind of consistent to what you have learned already, and that can be explained similarly. And also the rejection number needs to be very carefully determined, because we can see, say, for the two sampling inspection plan, the double sampling one, as we go on increasing ATI rejection number, the ATI decreases. This is because if we put the rejection number at a high value, then at each stage, the probability of acceptance will increase. And so 1 minus LP will decrease and the ATI will also decrease. So even increasing the rejection number can be a way of decreasing the ATI.
Interesting.
The rejection number is something we usually have it beforehand, but we can also determine it in some way. So the rejection number also needs to be determined carefully. So
you're right. But as rejection number decreases, it becomes flat after 2. That's what I'm saying.
Rejection number, yeah. Kind of with a similar logic as the cumulative acceptance. Like if rejection number is already very low, the probability of acceptance at each stage is itself low.
Absolutely.
So I have just explained the graph and the table. So yeah, that's where it kind of ends. Here we have the conclusion. So multi-sampling inspection is obviously very complex to administer. We took an hour to describe it. So, but it's of the benefit to the producer, because the ATI is a very important thing in describing the economic efficiency, because for each unit there's economic cost involved. So if ATI is less, then the overall cost becomes less. And also producer's risk can be compared similarly to ATI, because ATI here is N into 1 minus LP, and producer's risk is 1 minus LPT. So they will kind of go with similar values, but have not gone for producer's risk here, because without the N factor, it's kind of difficult to show the difference. So it also acts as similar to the ATI, and thus it also acts to the benefit of the producer. While keeping the consumer's risk fixed, we are not hampering the consumer's interests. So also, since like we have observed here, after enough high values of P, simply increasing the number of samples is not very beneficial. So we need to determine the optimal choice of number of samples in the multi-sample inspection plan. So this can also be a project idea, that the optimal choice of number of samples is the function of P. How to determine that?
But I think you have done a really good job in explaining using ATI that what is an optimum number of samples to be selected in the multi-sampling plan. So using a graph, just for example, in clustering algorithms, there is something like you can select the number of clusters based on similar Silhouette index or similar such thing. I think it's a really good deal, like on how to select the number of samples based on that graph. I think that's a really good way to do that. I think that's a really very good way. I think the two project ideas you mentioned that are mentioned during the conversation can be really beneficial for the students. But you have done a really good job in explaining how you can use this ATI to select what is the optimal number of samples. I think that's the best part of this, because that makes it clear that it's a very rock solid foundational project.
Because we have our first priority is the consumer, but we are keeping the consumer's fixed. So we now need to focus on our second priority, who is the producer. Because the producer's interests also need to be taken care of. And ATI kind of does the same thing. It takes care of the producer's interest while not hampering the consumer.
Okay, perfect. Super.
So this is it. And there's also some scope of further work where I have assumed the lot size to be significantly larger. This assumption could probably have been avoided and the calculation would have been more complicated, but it could have been done without the larger assumption. And then you won't have to stop at a particular k. You could just go on increasing k till the sample size exceeds the lot size. I had that restriction of stopping k at 6. You won't have it always. And there's another thing that I went for the acceptance rectification scheme. Someone could go for the acceptance rejection scheme and the ATA expression would change entirely.
Perfect. So thank you so much, Tathagata. It's an absolutely great pleasure in understanding from you. And yeah, can you stop sharing the screen so that we can just like be visible on the screen? It's showing an infinite loop. Perfect. So thank you so much, Tathagata, and thank you. And it was a lovely evening hearing from you and understanding from you. I hope these projects can be beneficial for the students to get motivated about the subject and know the dimensions, different dimensions it can go to, and also to give them ideas about future work that you have done excellently in your conclusion and future work options. So thank you for that. And I'm happy you have done such a great work. Okay. I learned a lot from you. See you soon and hope to work with you soon someday. Okay. All the best. Bye-bye.